All right, this is Saxon Algebra 2, lesson 57. We're on page 245, the ideal gas laws. Y'all have not done this in chemistry yet, right?
No.
You're probably about to. Here is the equation for the gas law. It's called the ideal equation, although my engineer boys would tell you there's really no ideal state. There's just a state where it's not combusting. Got it? Exploding.
Yeah, that's ideal.
Well, that's ideal if you ask me, right? Okay, we're not going to do all this today, but I do want to introduce this to you. P is the pressure. And if you look at the bottom of page 245, pressure comes in different unit measurements. A lot of it is newtons per square meter, but most of the time you're going to see atmospheres. Right? Okay, so that's pressure. V is volume. That's right. So volume, you see, is in liters, milliliters, or cubic centimeters. You know what? Have y'all dealt with moles yet?
Yeah.
Okay. N is moles. But you don't have to really understand it. You just have to know PV equals nRT. PV equals nRT. That's all you have to know. PV equals nRT.
We need to create like a little acronym.
R is a constant. It's never changing.
So it always says is R?
It's a value, which we're not even going to deal with today. But that's the value. I'm pretty sure that's the value. It's like pi. And that it doesn't change.
Guys, we know some.
Avogadro's number.
Yeah.
Wait, the R constant is 0.0821.
Yes.
Okay. Is there another name for it?
It's T times.
Constant. T is temperature. But that was a good guess. It's temperature. Temperature is in kelvins most of the time. All right, in order to keep this stable, if pressure goes up, then volume must go down if there's no change on the other side. So they're inversely, that's an inverse relationship. As one goes up and the other one goes down, that's called an inverse relationship. That's what we have when we have a linear equation that looks like that. That's an inverse relationship. As x gets bigger, y gets smaller. All right, so these are inversely related. Moles and temperature are inversely related. As moles goes up, in order to maintain equality, temperature must go down. All right? Now, pressure and temperature are related in the same way. They're not an inverse relationship. As pressure goes up, temperature can go up. Or as temperature goes up, volume can go up. That's what we see when we have a linear function like that. That's called a direct relationship. When one variable goes up and it causes the other variable to go up, that is a direct relationship. So we have two types of relationships. We have direct and we have inverse. Direct is when one variable increases, the other one increases. Inverse is as one increases, the other one decreases. Pressure is really the force on an area. All right, so something's going to happen as I increase the pressure on the inside of this balloon. Two things are going to happen. what happened?
It got bigger.
So the volume got bigger as pressure got bigger, but what else got larger?
Temperature?
The temperature. The temperature got larger. And it put pressure on the surface area of the balloon. So we have three things going up: pressure, volume, and temperature. And that is physics, actually.
No, not even
Physics is great. All right. For our purposes, so this is a whole lot more than what this lesson teaches you. All right. We are going to have two sets of values, and you're going to have to cross multiply and solve for one. We're going to say, assume the pressure, initial pressure volume, and I'm going to ignore those two. I'm going to ignore the constant and the number of moles. So if I have PV equals nRT, literally if I just ignore that, I'm dividing by T. So if I'm going to be given some information, a gas that is in an ideal state, and the pressure, the initial pressure, volume, and temperature of a gas. And then they're going to change two of the variables. So we have the initial PV over T equals a subsequent PV over T. How do I maintain this gas in an ideal state? If I change pressure and volume, what must the temperature be to maintain the ideal gas state? This is the formula. PV over T equals PV over T. That's it. PV over T equals PV over T. That's it. Look at example 1 on the top of page 246. 4 liters of an ideal gas. What's liters?
Volume.
Volume. That's my initial V. 4 liters of an ideal gas at a temperature, they tell you, 800 kelvins. That's in the denominator. Had a pressure of 100 newtons. PV over T. If the volume were increased, well, that's my sub 2. If the volume were increased to 10 liters and the temperature reduced to 600 kelvins, what must the subsequent temperature be? Okay, it's this easy, ladies and gentlemen. This is 400 over 800 equals 10 P2 over 600. This is 1/2.
What would be?
That's 1/2 equals, and I can get rid of a
Maybe
0.
30.
P2 over 60. And it is 30. You can cross multiply. 2P2 equals 60. Divide by 2. The subsequent pressure has to be 30. And what is our pressure in? It's in newtons. Newtons per square meter. Okay.
Is
So
that all?
although this is a complex concept,
It's simple.
the math is simple, right? We're just saying we have an ideal gas. We're changing two of the variables. What is the third variable? That's all you're solving for. And it's cross multiplication. I will say, if you can simplify. Do you have to simplify? No. You can cross multiply and use your calculator and get the correct answer. You just have to know PV over
T.
PV over
T equals nRT over T.
equals PV over T. PV over T equals PV over T for now. Got it? We're going to do equals nRT later.
Later today?
No. Later, probably next semester. All right. Example 2. The initial pressure. So that's my PV over T1s. Got it? the initial pressure of a quantity of gas is 400 newtons per square meter. And the initial temperature, it's PV over T, temperature's in the denominator, were 200 kelvins. Look at this. The volume was held constant. What does that mean? The volume doesn't change. If the volume doesn't change, it's just P over T. Because if the volume's 50 here, then the volume's going to be 50 here. So don't even use the variable that is unchanging. Does that make sense? What was the pressure? That's what we're solving for. What was the pressure if the temperature was decreased to what? 900 kelvins. Well, this is 1/3, right? 1/3 equals P2 over 900. Can anybody already tell me what P2 is? 300 newtons per square meter. Okay, do you have to just know that? No, you can do 900 equals 3 PT divided by 3. But how did they know it would be 300? Because there's a scale factor. You guys did this when you were much younger. Simplifying, you're used to going from 300 over 900, reducing it to 1/3. But now you're just making it bigger. So if 3 times 300 equals 900, then 1 times 300 has to equal P2. You see that? All right, I think there's one more example. Let's change colors. All right, the temperature of a, okay, what am I going to do with this? The temperature of a quantity of ideal gas was held constant. What am I going to do with that?
Just not have a denominator.
Just not have a denominator. It's going to be PV1 equals PV sub 2. Got it? We're not even going to look at temperature. It's going to be, got it? Okay. The original pressure, so we're just going to have PV equals PV because the temperature doesn't change. All right? The original pressure was 7 atmospheres and the original volume 42 liters. If the volume was reduced to 10 liters, what was the final pressure? Well, here you're just dividing by 10. What's 7 times 42 divided by 10?
29.4.
Is that right? 29, yes, 29.4 atmospheres. Got it? Okay. Because temperature was held constant, whatever variable was held constant, we're not putting it in our equation. So, normally we have PV over T equals PV over T. If temperature is held constant, we're going to not have temperature. This is when temperature is held constant. If pressure is held constant, then it's going to be V over T equals V over T. Make sense? If volume is held constant, then it's going to be P1 over T1 equals P2 over T2. And you're just substituting the values in that are given and solving for the one that's not, using basic algebra. Multiplication, division.